Hi, this is Dustin Yanofsky. We're doing discrete structures. That's the name of the class. We're up to section 2.2 of Ross and Wright, 5th edition, and it's called Propositional Calculus. This is basically about truth tables. Okay, so I have to tell you what truth tables is, but I want to motivate it from something you did in 9th grade. Okay, so in 9th grade you did something like this. Whoops. You did something like this. You said, okay, you have a variable x, you have a variable y, and you want to figure out what 3x plus 7y is. Okay, so you plug in a few numbers here. You say, okay, what happens if x is 1 and y is 2? So then you plug in 3 times 1 is 3, plus 7 times 2 is 14. 3 plus 14 is 17. Very nice. And you have if x is 2 and y is negative 1. So then let's see what you have. 3 times x, 3 times 2 is 6 plus negative 7. Negative 7. 6 plus negative 7 is negative 1. And then, but you could also do something like 500, and you could have this being 10. So let's see what that is. 3 times 500 is 1500 plus it's 10 times 70, y is 10, so 7 times 10 is 70, plus 70 is equal to 1570. Okay, and you can do this for an infinite amount of things. Okay, so what are you doing here? You're plugging in numbers into this thing. You want to figure out what this is equal to. Well, it depends on what x is and what y is. Okay, it depends on what x is and what y is. So you can put in a lot of different values for x, and you can put in a lot of different values for y, and every time you put in a different value for x and y, you're going to get out a different value for 3x plus 7y. Great. Now, what we're going to do is as follows, but the way to think about this is, you know what 3 times x plus 7 times y is? Those are operations that you did to x and y. You multiplied it by 3, you multiplied it by 7, you added them together. Those are operations. We're not interested in numbers. We're not interested in things like this. This is what you did in 9th grade. We're interested in things like this. Not P, arrow, Q or not S. Okay? Take this whole thing and say this is biconditional to Q and R. Let's make that small. Let's make that S plus P. Okay, something like that. This is a logical formula. Okay, and you might say, what's its value? And you say, well, it's very simple what its value is. You tell me what P is, you tell me what Q is, and I'll figure it out. Okay, so we make truth tables. Okay, and we say, oh, P and Q and S. Okay, now we want to know what those values are. But logic is a lot simpler than that. Why is logic simpler? Because logic, we don't have all these possible values to put in here. Logic, P can either be true or not true. It's a proposition, so it's either true or not true. As opposed to x, x could be 1, x could be 2, x could be 500, x could be 400, x could be 382.76. Okay, those are a million values. But P here can either be 0 or 1. Q can either be 0 or 1. S over here can either be 0 or 1. So we have to put in all those possibilities. But logic is much simpler because we don't have to worry of that many values. It's only true or false. That's the only thing a proposition can be, true or false. So we don't care about numbers. Numbers are painful, hard. Okay? Logic is easy. Okay? So that's what truth tables are all about, and we're going to start making truth tables right now. Okay? Okay, so let's start with something easy. Okay? So let's say I tell you P stands for I like ketchup. Okay? And now I want to know, what is not P stand for? Well, not P stands for I don't like ketchup. Very good. I don't like
Don't listen to that.
ketchup. Okay, very good. So I like ketchup or I don't like ketchup. You want to go upstairs and make sure everything is okay? Okay, fine. Okay, great. Now I want to know, is not P true or false? So we're going to make a truth table for not P. Okay, there are two possibilities. Now I ask you, is P true or false? Okay, so it depends. I'm sorry, let's do that again. Is not P true or false? Well, it depends. What's P? Well, P can only be two things. Either I don't like ketchup, so 0 is false, and 1 is true. Okay, so we're going to have that always. So if it's 0, then what is not P? So let's say, if it's false, if I don't like ketchup, okay, P stands for I like ketchup. If that's false, then the statement I don't like ketchup is true.
Don't listen to that in the background.
I think that's more what
Okay,
it is.
if P is true, I like ketchup, then the statement I don't like ketchup is false. Okay, so that's the world's smallest truth table. Okay, 0, 1. Now we're always going to put 0, 1. We're always going to put it like that. Great. Let's look at other truth tables for other statements. Okay. Okay. Let Q stand for I like mustard. Do you like mustard?
No.
Nobody likes mustard, but okay, fine. So then we could talk about P and Q. Okay, okay. And now I ask, when is P and Q true? And the answer is, when P is true. What does the P and Q mean? It says, I like ketchup and mustard. Okay, when is it true? Well, it's true when you like ketchup and you like mustard. Otherwise, it's not true. So let's go through. Let's put all possible values for P and Q. Okay, we're going to put all possible values just like we did for the numbers, but the numbers we couldn't finish making the list because there were only infinite number of numbers you could put in. But here you can do it. And I'm going to do this in a special order. 0, 0, 0, 1, 1, 0, 1, 1. Okay, and now we ask the following. P and Q. If I don't like mustard and if I don't like ketchup and I don't like mustard, then this statement, I like mustard and I like ketchup, is false. If I don't like ketchup, but I like mustard, then the statement, I like ketchup and mustard, is also false. Okay, because this says you like both of them. If I like ketchup, if it's in fact true that I like ketchup but I don't like mustard, then the statement, I like ketchup and mustard, is also false. When is it true? Only if you like ketchup and you like mustard, then it's true. Okay, go.
Or if you're having a hot dog.
Oh, very good. Okay, next, I want to talk about some other operations. P or Q. Okay, when is this true? What does it mean? I like ketchup or mustard. Okay, well, if I don't like either of them, then the statement is false. I don't like ketchup, I don't like mustard, then the statement, I like ketchup or mustard, is false. But if I like one of them, the truth is, I like ketchup, I don't like mustard. That's the truth.
Yeah.
Okay, in that case, this thing, I like ketchup, but I don't like mustard, well, the statement, I like ketchup or I like mustard, is true. Okay? By the way, let's say today is Tuesday, and then the statement, today is Tuesday or I am a billionaire, is a true statement. Okay, because one of those things is true. Today is Tuesday or I am a billionaire is a true statement. Why? Today is Tuesday and
It's Monday.
well, okay, whatever. If today is Tuesday, then it's a true statement. Okay, you need only one of them to be true. So here you like mustard, that's true. Here you like ketchup, that's true. Here you like mustard or ketchup, that's true. Okay, great. Now let's do another operation. Let's say P implies Q. Now this is the hard one. This is the one that people don't like. Let's talk about it. If I tell you if you go more than 50 miles an hour, you'll get a ticket. And you go more than 50 miles an hour and you get a ticket, then what I said is true. Okay, let's go through this. If you go more than 50 miles an hour, then you'll get a ticket. You went more than 50 miles an hour and you got a ticket. So my statement is true. Now, let's say it happens here. You go more than 50 miles an hour and you don't get a ticket. Then my statement, if you go more than 50 miles an hour, you'll get a ticket, that's false. It's a false statement. Okay? That's this if-then statement. Okay? If the first thing is true and the second thing is false, then it's false. The statement is false. Okay, what about these two? Let's say I tell you, if you drive more than 50 miles an hour, you'll get a ticket. And you don't drive more than 50 miles an hour and you don't get a ticket. Is my statement true or false?
True.
Okay, so we're going to do it that it's true. Because I wasn't shown to be false. I tell you, if you drive more than 50 miles an hour, you'll get a ticket. You'll get a ticket. Same thing, let's talk about the rain and the clouds. I tell you, if it's raining, then there are clouds in the sky. Let's say there are no clouds in the sky and there's no rain. Did I say something false? No, I said something true. If there's rain,
There's clouds
there's clouds.
that are going away.
Right. Okay, let's go this way. Let's say I tell you, if you drive more than 50 miles an hour, you'll get a ticket. You don't drive more than 50 miles an hour, but you still get a ticket because there's a crooked cop or because you have a broken tail light or something. But anyways, my statement is still true. The only time my statement is false is if I say this implies this. This is going to give you this, and this is true and this is false. If that's what happens, the first thing is true and the second thing is false, then that's false. Okay, great. Let's do another operation. Okay, how about this? P plus Q. Now this is exclusive or. This is true or this is true, but not both. Okay, so if, let's see, I like ketchup or mustard, but not both. If I don't like ketchup or mustard, then this is a false statement. If I like mustard but not ketchup, this is a true statement. If I like ketchup but don't like mustard, it's a true statement. The only thing that's different is if both of them is true, then this statement is false. Look what this statement says. I like this one or this one, but not both. And if both of them is true, then it's false. Then this statement is false. Notice this is the inclusive or. That includes both. This is the exclusive or. Okay? The only difference is here. Okay? 0, 1, 1, 0, 1, 1. Here's a 1, here's a 2. If both of them are true, this is 1. If one of them is if both of them are true here, it's false. Okay.
Why is it a plus if it can't be both?
Right. Okay, good. Good question. Let's do one more operation. Okay, sorry, we ran out of room. Let's do one more operation. P double arrow Q. Okay. Okay. What does this say? This says P implies Q, Q implies P. Let's give you two examples for this. I did this last time. Let's do two examples. If today is Tuesday, then tomorrow's Wednesday. Okay? If tomorrow's Wednesday, then today is Tuesday. Let's go through it. If today is not Tuesday and tomorrow's not Wednesday, okay, then this statement is true.
It's false.
No, it's true because they're both the same. What this says, double arrow, means this is the same as this is the same as this. So when they're both zeros, they're the same. If today is Tuesday and tomorrow is Wednesday, so then this statement is true. The only time it's not true is over here. If today is not Tuesday, but tomorrow is Wednesday, then the statement, today is Tuesday, if and only if tomorrow is Wednesday, is false. So these two are false. Okay? What the double arrow means is they're both the same. They're both the same. Okay, great. Okay. Let's do some examples. Okay? So great. So we now know this is the building blocks for for truth tables. Now we're going to start building bigger truth tables. So let's build bigger truth table. Not P, arrow, P and Q. Okay? So this is a logical statement. It consists of operations that we build up things, just like we build up with numbers. Okay, we build up things. Okay, so question, what is the value of this? Well, the answer is, it depends. What is P and what is Q? So we have to plug in all possible values of P and Q. We always write our variables in alphabetical order, and then we put them in with zeros, all zeros starting at the beginning. 0, 1, 1, 0, 1, 1. Okay? For those of you who know binary, this is the number 0 in binary, the number 1 in binary, the number 2 in binary, the number 3 in binary. So we do it like this. This is good for computers. Okay, great. Now, I want to know what this value of this thing is. Well, in math, you always have to work from the inside parentheses first. So let's work on the inside of the parentheses. So, not P. By the way, I do this slightly different than the book. If you want to do it following the book, that's fine. You could follow the book, but I do this slightly P. Not slightly different than the book. Doesn't matter. It's the same with the same result. Not P. What is not P? Again, I don't know what P stands for. I don't know what Q stands for, but P can have one of two values: 0, 0, 0, 0, or 1. So not P would be what? If this is 0, then this will be a 1. If this is 0, this will be a 1. If this is 1, this will be a 0. If this is 1, this will be a 0. That's what not P is. Now let's do what P and Q are. Okay? P and Q is true only when they're both true, down here. If one of them is true, or the other one is true, or none of them is true, it's 0. Great. Now I'm going to do the arrow. So now I want to know what the value of this is. I did the value of this. I did the value of this. The final answer is this. Okay, great. Now we have the arrow. Let's go through the arrow. If the first part is true and the second part is false, is it true or false? And the answer is it's true. It's false. Okay, what is the arrow? It says it's only false if this is true and this is false. Otherwise, it's always true. First part is true. Second part is false. 0. First part is false. Second part is false. True. First part is false. Second part is true. True. Okay? And this is the final answer of the truth table. Okay? This is the final answer of this part. This is the final answer of this part. This is the final operation. So this is the final answer of that part. Okay? Sounds good? Okay, let's do another one. Okay, you ready? So we're going to do A plus B arrow, not A or B. Wow. Okay. Okay. Let's link up the parentheses here. This links up with this. This links up with this. This links up with this. Okay. So, in order to solve this, we have to give all possible values for A and B. So let's do that. 0, 0, 0, 1, 1, 0, 1, 1. Okay, now we do it. Now how do we do it? You do what's in all math, you do what's inside the parentheses first. So, not A. What's not A? So, first, we have to do this. Okay? In order to do this, we have to do this. In order to do this, we have to do this. In order to do this, we have to do this. Not A. So, what's not A? Okay, I'm going to take A and I'm going to flip it. If it's 0, I'm going to make a 1. If it's 0, I'm going to make a 1. If it's 1, 0. If it's a 1, 0. Great. Now, B. I'm going to rewrite B over here. 0, 1, 0, 1. I just rewrote B. And now I'm going to do OR of it. What is OR? It has to be one or the other has to be true. So let's do it. 1 or 0 is true. 1 or 1 is true. 0 or 0
is true.
No, false. 0 or 1, 1. Okay, great. So we now have the final answer for this inner parentheses. Great. Now we do B. You ready? So let's rewrite B. 0, 1, 0, 1. And now I'm doing the single arrow. You know what? And just to make it a little bit different because we did the single arrow already, let's do the double arrow. Okay, so let's just remember what the double arrow says. If they're both 0, it's true. If they're both 1, it's true. If the inputs are different, it's false. Okay, so let's do it. You ready? So now I'm comparing to get this. I put it like this. I'm looking to solve for what's under this double arrow. Okay, so let's do it. You ready? 0, double arrow 1. 0, double arrow 1 is 0. Why? Because they're different. 0 and 1 is different. 1 and 1 is the same, so it's true. 0 and 0,
False.
1. 1 and 1, 1. Good? So now, this is the outermost operation for this thing, and now we have to do the plus. So let's go through. Let me just rewrite A. 0, 0, 1, 1. Okay, and now plus. Let's remember what plus is. It's like or, one or the other, but not both. Remember? So let's do it. 0 plus 0 is what?
0.
0. Good. 0 plus 1 is 1. 1 plus 1. Uh-oh, exclusive or. 1 plus 1. 0. And 1 plus 1.
0.
0. Okay? And so our final answer is right here. Okay, great. Okay, great. Now let's do the big boy stuff. Before we do the big boy, let me just do one other thing. I told you last class that P arrow Q is the same as, okay, we wrote the same as like this, not P or Q. Okay, now let's go through this with our example of driving faster than 50 miles an hour. If you drive faster than 50 miles an hour, you'll get a ticket. That's the same as don't drive faster than 50 miles an hour or you'll get a ticket. Now I'd like to show you why these two things are really the same. The way I show it is as follows. I'm going to put both of them on a truth table. Okay, here's the variables P and Q. I'm going to put P arrow Q over here. I'm going to put not P or Q over here. And what I'm going to show you is they make the same truth table. That means whatever's true over here is true over here. Whatever's true over here is true over here. So let's go through it. Let's put possible values for P and Q. 0, 1, 0, 0, 0, 1, 1, 0, 1, 1. Okay? Okay. Now let's do P arrow Q. When is it false? It's only false when the first thing is true and the second thing is false. That means it doesn't imply that. So here it's false. Everything else is true. Great. Now let's do this one. You ready? It's like this. Not P. What's not P? 1.
1.
1.
0, 0.
0, 0. Great. And Q, I'm going to rewrite Q. 0, 1, 0, 1. And now we're going to do the OR of it. So you ready? 1 or 0. 1. 1 or 1. 1. 0 or 1. 0 or 0. 0. 0 or 1. 1. Now, hold on. Look at that. 1, 1, 0, 1. 1, 1, 0, 1. These are the same thing. Exact same thing. Okay, so it shows that these two things are the same thing. Okay? Okay, great. Now, let me show you what we're going to do next, because we have a lot to do. Okay? This is fine for two variables, PQ, AB. What happens if we have three variables? So let me give you an example. Okay? P, double arrow, let's do this, not P, double arrow, Q, and not R. Okay, that's a capital P. It shouldn't be a capital. We're going to be doing all small letters. P. Okay? Okay, so that's a simple three variable thing. P, Q, and R. Okay? Okay, let's do this. This is the innermost operation. Now, we have to describe all the possible, you might ask, is it true or false? Well, let's say the answer is it depends what P is, it depends what Q is, it depends what R is, right? So what the output for this whole thing depends on these things. So P, whoops, small letters, P, Q, R. Okay, now I want to give all possible values for P, Q, and R. Every single possibility of zeros and ones. So let's do it. You ready? 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay, now every possibility is there. Every possibility of what P is and what Q is, they're all there. Okay, great. Now, I want to fill in this form, this thing. So let's do it. First, let's do not P. Okay, so this is the final operation. I want to do this. First, let's do not P. Not P is very simple because P is 0, 0, 0, 0, 1, 1, 1, 1. So what's not P? 1, 1, 1, 1. By the way, you have this easy because you're writing on paper. I don't have this easy because I'm writing without lines. So I'm going to have to draw this line. This line is just for me because otherwise my answers start waving because I'm not so neat. So I need that line. Okay, if P is 1, what's not P?
0, 0, 0.
0, 0, 0,
0.
0. Great. Okay, now let's do this side. In order to do this side, we have to do what's inside there first. Let's do not R. So let's do not R. So R is 0, 1, 0, 1, 0, 1, 0, 1. Not R is 1, 0, 1, 0, 1, 0, 1, 0.
The total opposite.
The total opposite. Exactly. That's exactly what not is, the total opposite. Okay, good. Let's rewrite Q over here. So Q is 0, 0, 1, 1. 0, 0, 1, 1. Okay, and now end. 0 and 1, 0. 0 and 0, 0. 1 and 1, 1. 1 and 0, 0. 0 and 1, 0. 0 and 0, 0. 1 and 1, 1. 0 and 1 and 0, 0. Okay, great. Now I have to compare the final result of this, that's this, and the final result of this is and. Okay? And I have to do it under the double thing. So I need 3 fingers to do this. Ready? 1, double arrow 0 is what? They're different. 1 and 0 are different. What is it? 0, exactly. 1, double arrow 0 is? 0. 1, double arrow 1 is?
True.
True. 1. 1, double arrow 0 is?
0.
0. 0, double arrow 0, 1. They're the same. They're the same. They're different. They're the same. Okay, and so we get our final answer right over here. This says, what's the value of this proposition? Well, it depends what the input is. If this is the input, then that's the output. If this is the input, then that's the output. If this is the input, then that's the output, etc. Okay? We're going to do another 3-valued one in a second. First, we have to say goodnight from the peanut gallery. Come here, peanut gallery. This is Miriam. She's saying goodnight. Okay, do it, Hickey. Okay, you coming? No, he's not coming. All right. Anyways, we're going to take.
That's it.
Oh, okay. Hi, my name is Baruch Yanofsky. Okay, see you around. We're going to do this in 1 second. Okay, continuing along the way, I want to do something that we didn't do before. I want to give you a cheat sheet. Okay, and then we'll do it while we'll do another example with that cheat sheet in mind. Okay, we like cheating. So I'm going to put up all the operations here. You cannot bring in a cheat sheet on the test, but you should be able to make it yourself. So if you have P and you have Q, okay, let's look at all the possible operations you can have. You can have P and Q, you can have P or Q, you can have P exclusive or Q, you could have P arrow Q, you could have P double arrow Q. Okay, let's see what possibilities we have. This is 0, 0, 0, 1, 1, 0, 1, 1. Okay, and we're going to keep this small, and we're going to keep this cheat sheet around. So 0, 0, false and false, 0. Let's go, everybody. 0 and 1, 0. 1 and 0, 0. 1 and 1, 1. What about or? When is or true? When one or the other one is true. So let's see.
0, 1, 1.
0, 1, 1, 1. How about exclusive or?
0, 1, 1, 0.
0, 1, 1, 0. How about arrow? We've said arrow this is false only when the first thing is true and the second thing is not implied. So every other thing this is true. So it's 1, 1, 0, 1. How about double arrow?
Double arrow is 1, 0, 0, 1.
Right. When they're the same, 0 and 0, it's a 1. When they're the same, 1 and 1, it's a 1. When they're different, that means one doesn't imply the other, 0, 0. Okay? Okay, by the way, there's other operations, and I want to talk about one other operation. It's called the Sheffer stroke. Okay, but we know it from another name. Okay, and it goes like this. Given P and Q, I'll tell you what the other name is in a second. You have P, Sheffer stroke, Q. Okay, and so let me show you how it's defined and why it's important. Okay, and why you'll see it again. This is 1, 1, 1, 0. Okay. Okay. Now you're going to see this later on, or when you take architecture class. This is also called the NAND gate. What's NAND? Okay. So, and we understand. This is not and. Okay, so this is basically the same thing as this. P and Q, okay, but not that. Okay, so let's see how that works. P and Q is what? 0, 0, 0, 1. That's what and is. Now you do the not of that, and you switch around what you have.
1, 1, 0.
1, 1, 1, 0. That's the same thing. Okay, so the Sheffer stroke is also called the NAND gate. Okay, now it's used in all computers. Your computers are made out of a lot of gates, okay, AND gates, OR gates, whatever. Computers are engines of logic. They do exactly what logic tells them to do. If electricity is going through this wire and electricity going through that wire, and there's no electricity going through that wire, then send electricity through that wire. That's a typical thing of the way computers work, okay? But it turns out that you can, with these gates, NAND gates, you can do all these different things. So your computer is really made out of a lot of NAND gates, just NAND gates, okay? So when somebody asks you what's in your computer, you say NAND gates, okay? Which is the Sheffer stroke. Okay, great. I want to do one more example. We'll keep our cheat sheet up, and I want to do one more example, but I want to do it in two different ways, okay? I'm going to do it the way we always been doing it, and then I'll do it in a new way. So let's do it this way. So here's a nice example. It's going to have 3 variables. So how many rows does it have?
3.
No, how many rows does it have? It's going to have, for each of the 3 variables, it could be true or false, true or false, true
2.
or false. So 2 times 2 times 2 is 8. Okay, good. So, not P, arrow, R or S. Okay, let's do that in square brackets. Okay, I'll put that in brackets. Okay, and S arrow, not R. Okay, so there's 3 variables, P, R, and S. Okay, and we're going to do this. Now, all this is in these. All this is in here. So our final answer will be here, under this AND. That's going to be our final answer. Okay, and we can do this first. We can do this first. etc. I'm going to do this the same way we've always been doing this, but with a little bit quicker. So let's put down our variables in alphabetical order. PRS, sorry, no Q, PRS, PRS, okay, and let's do it. And then we're going to do it another way. Okay, so now we put in all possibilities of what the variables can be. You ready? 0, 0, 0, let's go everyone, 0, 0, 1, 0, 1, 0, 0, 1, 1. Okay, the way to see it is, here you change every other one. 0, 1, 0, 1. Here you change every two. 0, 0, 1, 1. Here you change 0, 0, 0. You're going to have 4 of them, and you're going to have 4 ones. Okay, here this continues going. 0, 1, 0, 1. And this is 0, 0, 1, 1. Okay, this gives me all 8. And like I explained before, I need to put this line, otherwise I get sloppy. Okay, good. Let's do it. So, I want to get the final answer. The final answer will go right over here. Okay? The final answer will go here because that's the outermost operation. But in order to get to that, I have to do what's on the left and I have to do what's on the right. In order to get to what's on the left, I have to do the outermost operation is going to be over here. But let's do not P. So let's do not P first. Not P is simple. You ready? 1. Here's P. I'm going to do not P. Are you
1, 1, 1, 4 ones.
okay? And then
0, 0, 0, 0. That's not a password.
okay, good. Next, how about R or S? Now I can sit there and I can rewrite R over here, and then I can rewrite S over here. But you know what? It's right over there, so I don't have to rewrite it. Let's just do the OR. You ready? 0 or 0. Well, we can cheat. 0 or 0 is 0. 0 or 1. I don't hear a lot of helpers here. 0 or 1 is 1. 1 or 0. 1. 1 or 1. 1. 0 or 0. 0. 0 or 1. 1. 1 or 0.
1.
1 or 1. 1. Okay, great. Now, I'm trying to do this. I did this part. I did this part. Now I have to do the arrow. Okay, let's remember the arrow. The arrow says everything is 1 except if the first thing is 1 and the second thing is 0. That's the only time. So let's do it. 1 arrow 0. 1 arrow 0.
1, 0.
0. Okay. 1 arrow 1. 1. 1 arrow 1. 1. 1 arrow 1. 1. 0 arrow 1. 0.
0.
Okay, now here's a trick. You ready? This is called lazy evaluation. My kids don't clean their room, so they're lazy. They love this trick. The trick is as follows. Look. Let's look at the arrow. One thing I can tell you, if the first thing is 0, I don't care what the second thing is, it's always going to be 1. So I don't have to, when I'm looking at this 0 arrow, I don't have to look at what the output is, what the second thing is. Because 0 arrow anything is 1. So watch this. 0 arrow anything is 1. 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 That's called lazy evaluation. You don't even have to look at this part. You can evaluate it without looking at it. Okay, great. That takes care of the left side. Now we have to do the right side. You ready? S arrow, not R. So let's do not R. You ready? Not R is, here's R. We're going to do not R. You telling me? Ready? What do we get?
0, 0, 1, 1, 0, 0, 1.
That's R. What's not R?
1, 1, 0, 0.
1, 1, 0, 0. 1, 1, 0, 0. Okay, great. Now we have to do S arrow, not R. So I can rewrite S over here. If you want, we can do that. We can rewrite this right over here, and then we'll do the arrow. But you know what? It's right there, so let's do it. 0 arrow 1 is 1. Okay, I don't even have to do that. 1 arrow 1 is 1. 0 arrow, I don't even have to look. Lazy evaluation, my favorite word. 0 arrow anything is 1. 1 arrow 0 is 0. 0 arrow 1 is 1. 1 arrow 1 is 1. 0 arrow, I don't care what, is 1. 1 arrow 0 is 0. Okay, almost done. Okay, now I got to do the final operation. In order to do the final operation, I take the final answer here and bring it here. I take the final answer here and bring it here, and we do it. You ready? Okay, ready? So this is an AND operation. Let's do it. I need 3 hands to do this. 0. Miriam, you want to help?
Yeah.
Okay, Baruch will do it. Okay.
You're
Baruch will you do the first one. You ready? I'm going to point to it. You can put the output. You ready? 0 and 1. 0. 1 and 1. 1. 1 and 1. 1 and 0. 0. Great. 1 and 1. 1. 1 and 1. 1 and 1. 1 and 0. Very good. Okay, great. Okay, so we did, that's the final operation. Okay, great. I want to do this, but I want to do it in another way also. Okay? So that's the final operation. Very nice. Etc. Okay, let's go through another operation. Now, the book does it this way, the way I just did it, but they also do it another way, and you might have seen it the other way. I see that high school students do it the other way, so let's do it. They say like this: okay, you want to evaluate it? Let's evaluate it one at a time. Okay, so let's first figure out, you know what? I'm going to write the problem over here. Not P, arrow, R or S, okay, and so this is square brackets. We'll put a round bracket here. We'll put a round bracket here. And S arrow, not R. Okay, that's the problem. By the way, the square brackets and the round brackets doesn't mean anything. It doesn't. There's no difference. I just want to separate them. Okay, great. So now I'm going to do it like this. What they do it is, instead of having the chart all the way there. Okay. And there's another way that the book does these things, and I wanted to spend a minute making sure that we understood it. We're pretty straight. Okay, so here's the same thing we did last time. So the book does it, instead of writing out everything and then putting everything underneath, it does it one at a time. So let me show you. So first thing I will do is not P. Okay, so that's the first part of it. So not P would be 1, 1, 1, 1, 0, 0, 0, 0. Okay, good. Then it says, okay, now figure out R or S. So it'll do, so we'll put a line there, R or S. Okay, so now we have to do R or S. Well, we know R or S, or, here's our cheat sheet for or, and so we put it in. You ready? It's when one or the other is true, but not both. So, but when one or the other or both is true. So it's 0, 1, 1, 1, and here it's 0, 1, 1, 1, 0, 1, 1, 1. Great. And now it's going to do the arrow in between them. So you're going to have not P, arrow, R or S. Okay? And so now what you do is 1 arrow 0 is 0. 1 arrow 1 is 1. 1 arrow 1 is 1. 1 arrow 1 is 1. 0 arrow anything 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 is 1. Great. That takes care of this part. Okay? So what you're doing is, instead of putting it all down on one big chart, you're developing the chart slowly and you're bringing it along. And you're doing it step by step. Okay, so now let's continue. We have to do this side. Great. What's this side? Well, the first thing to do is this not R. So let's do not R. Okay, so not R is flip R. So you have that as 1, 1, 0, 0, 1, 1, 0, 0. Okay, great. And now we're going to do S arrow not R. Okay, so I'm going to S arrow not R. So 0 arrow 1 is 1. 1 arrow 1 is 1. 0 arrow anything is 1. 1 arrow 0 is 0. 0 arrow anything is 1. 1 arrow 1 is 1. 0 arrow anything is 1. 1 arrow 0 is 0. Okay, great. So now we have this part, which we did over here. We have this part, which we did over here. Maybe I'll put a thing around it. And now we have the final thing. So I'm just gonna, usually you have to do this in a long piece of paper, but instead I'm just gonna write it here, okay? And basically that's what you build towards the final answer. And what's the final answer? It's this and this. This, that's that, and this. Okay, so let's do it. All right, and so we have 0 and 1 is 0. 1 and 1 is 1. 1 and 1 is 1. 1 and 0 is 0. 1 and 1 is 1. 1 and 1 is 1. 1 and 1 is 1. 1 and 0 is 0. Okay, and that's your final answer. Okay, so it's just two different methods of how you do this. I prefer the way I did it before first, but the book gives you this method also, and it's fair and it's nice. Okay, so that's the end of. It's not the end of truth tables, but it's the beginning of truth tables. But I promise you, on the tests and on the midterm, you will definitely have a truth table to do. Okay, it's one of the things you have to walk out knowing from this class. So we're going to do it. Great. A few more topics from section 2.2. Few more topics. Okay, there are 3 types of logical formulas. One is called satisfiability. Satisfiable. Satisfiable. And what that means is the final result, the final column has at least one 1 in it. Okay? So what that means is, it could have many ones. What that means is that you have a logical formula. You want this to be true, you want that to be true, you want that to be false, etc., so that the final result, there's at least one 1 in it. Which means that somewhere in those lists of P, Q's, and R's, there's some way to satisfy the formula. Okay, there's some way to satisfy that formula. Okay, if you can satisfy that formula, if you can make it true, then it's called satisfiable. Okay, every single truth table that we had so far has been satisfiable. There's been at least one 1 on them. There's some way to make it true. Okay, in contrast to that, we have something called a contradiction. Okay, what's a contradiction? Okay, the final column has all zeros. There's no way to make this true. Okay, every single thing, no matter what the values of the formula of the variables are, true, 0, 1, 1, 0, whatever, anything, doesn't matter. The final result is false, 0. Let me give you an example. if I say A implies B and B implies C, okay, if A implies B and B implies C, okay, and A is true and C is false. Okay. Now, you can already see that there's no way to satisfy this, but let's just go through what this says. This says if A is true, then B is true. If B is true, then C is true. Okay? A is true and C is false. Okay? Let's actually write out the truth table for this. A, B, C, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. Dotted lines. Again, why do we do the dotted lines? Because you have lines on your paper, you don't need it, but I do. 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay? And we're going to go through this. Okay, I'm going to make sure, whoops, can't see all the way to the bottom. Okay, let's do it. Okay, so A arrow B is, I'm just going to do this a little bit quickly because there's a matter of time here. 0, 0, 0, so that anything that starts with a 0 is 1. So this is 1, 1, 1, 1. Sorry, not size appropriate. 1, 1, 1, 1. And then 1, 0, this is 0, 0, 1, 1. Okay, let's do B arrow C. 0, 1, 1, 0, 1.
1, 1.
1, 1, 0, that's 1 arrow, 0, 1. Okay, good. Okay, great. Let's do the AND of these. So what's the AND? 1 and 1 is?
1.
1 and 1 is what?
1.
1 and 0 is?
0.
0. 1 and 1 is what?
1.
0, 0, 0, 1. Very good. Okay, now let's do not C. Okay, let's do not C. So not C is what? Not C is 1, 0, 1, 0, 1, 0, 1, 0. Okay, A, let's rewrite A. That's 0, 0, 0, 0, 1, 1, 1, 1. Okay, now we're going to do AND of it. So this is going to be 0, 0, 0, 0, 1, 0, 1, 0. Great. And now we're going to bring together these two things. The final thing of this first part is under the AND. So we're going to bring this together, and we're going to bring this together. Okay, and we're going to do AND of it. Okay? So let's do it. You ready? 1 and 0 is 0. 1 and 0 is 0. 0 and 0 is 0. 1 and 0 is 0. 0 and 1 is 0. 0 and 0 is 0. 0 and 1 is 0. 1 and 0 is 0. All zeros. That's a contradiction. That's absolutely a contradiction. Okay, so that's an example of a contradiction. Let me give you a shorter example of a contradiction. Ready? This is the world's shortest example of contradiction. Can't get shorter than this. Ready? P and not P. Okay? Okay? I like mustard and I don't like mustard. Okay, well, P is either true or false, 0 or 1, it's false or true. Okay, so let's write this out. This is 0 or 1, this is 1 or 0. Okay, let's do AND of it, 0, 0. That's a contradiction. There's no way you're going to make P and not B be true. Okay? Okay. So that's a contradiction. There's lots of other examples of contradictions. There's a third type of thing, and it's called tautology. Tautology should remind you of the word total, which means all. Okay, so tautology, the final column has all ones. Everything is true about it. Okay, it's always true. So let me give you some examples of tautology. First, the easiest example of tautology, P or not P. I either like mustard or I don't like mustard, one or the other. Okay, so let's go through it. P is either 0 or 1. Here we have 0 or 1. Not P is 1 or 0. Okay, what is it? 0 or 1 is 1. 1 or 0 is 1. That's a tautology, all 1. Okay? Let's do a more complicated tautology, just a bigger tautology. Okay, and I need more room. So we'll remember these words. Okay, let's just go through them. Satisfiable means at least 1 0. Contradiction means all 0. Satisfiable means at least 1 1. Contradiction means all zeros. Tautology means not only 1 1, but all of them are 1. Okay, and the way to think of this is, here's all logical statements. Okay. Some of them are satisfiable. That means you can make it true. They can be satisfied. Some of them are contradictions. That means you cannot make it true. Okay? And a subset of the satisfiables are those that not only can you make it true, but it's always true no matter what. We call those tautologies. Okay, so now you have all 3 of them on one nice little, makes sense. These have at least 1 1s. This has all 1s. This has no 1s. Okay, let's do another example of a tautology. Okay, along the lines of the same thing that we did last time. So we say as follows. You ready? A arrow B and B arrow C implies A arrow C. Let's say it in English. If A implies B and B implies C, then A implies C. Okay? If you study, you'll get good on the grades. If you get good on the grades, you'll be happy. So if you study, you'll be happy. Makes sense? Okay, so let's just do it quickly. Again, it's going to take a few minutes, but okay, 0 0 0 0 0 1 0 1 0 0 1 1. Okay, 1 0 0 1 0 1 1 1 0 1 1 1. Okay, A arrow B. Miriam, you helping me? A arrow B.
0.
0 arrow 0.
1.
1 1 1. 0 0 1 1. Great. B arrow C is what?
0.
1 1
1.
0 1 1 1 0 1. Okay, now let's do AND of it. 1 and 1 is 1, 1 and 1 is 1, 1 and 0 is 0, 1 and 1 is 1. This has a 0 in it, so it's 0. This has a 0 in it, so it's 0. This has a 0 in it, so it's 0. 1 and 1 is 1. Okay, good. Now, A and C. Ready? A and C. 0 arrow 0 is 1. Anything, a 0 arrow anything is 1. 1, 1. Good. 1 0 0. 1, 1, 1. 1, 0, 0. 1, 1, 1. Great. And now we're going to bring this together with this, and we're going to do the arrow. Ready?
1.
1 arrow 1 is 1. 1 arrow 1 is 1. 0 arrow anything is 1. 1 arrow 1 is 1.
1.
All these starts with zeros, right? So 1, 1, 1. 1 arrow 1 is 1. All ones. Tautology. Always true. It's always true that if A implies B, not only about studying and about happiness, but no matter what, if A implies B and B implies C, then A implies C. Okay? So those are 3 things you've got to know. I promise you on a test I'll say, is this satisfiable? Is it a tautology? Is it a contradiction? And you have to show me. Okay, great. Okay, we need a definition, new thing. So we're going to use truth tables, but we need a new thing. So let's say definition. That's definition. 2. The book does this, and the book is very, very exact about the words. I'm a little less exact, but once you see what I'm talking about, you'll be able to figure out what the book's talking about. 2 compound propositions. That means they're propositions, but they come from ands and ors and arrows and double arrows and symmetric difference and whatever, exclusive ors, etc. Okay, 2 compound propositions, P and Q, are logically equivalent. Okay, logically equivalent. That means they're equivalent, they're equal. Equivalent is another word of saying equal, but they're equal logically. Okay, it doesn't mean they're equal, they're the same sentences. Remember, proposition is a sentence that's either true or false. We're not saying that they're the same sentence, but we're saying that logically they're the same thing. And I'll explain to you exactly what it means. If they have the same truth values for all the variables. Okay, I'll explain to you what. Period. Okay, that means, look, these 2 formulas, they're made up of different variables. Well, if you plug in the same true or false into these variables, and you plug in the same true or false into these variables, you get the same final result. So again, they're not the same statement, but they're logically equivalent. Let me restate this. That is, okay, that's another way of saying it. The final outputs of both truth tables are the same. Again, no matter what you put in for the variables in this one, what you put in for the variables in this one, they'll be the same. Okay, so the truth tables are similar. Okay, we write it like this: P with double arrow, Q. Double as in both ways, and also double, it's not just one line there, it's 2 lines. Okay, let me say it a third way. Okay, let me say it a third way. P double arrow Q. Very important. This is not a logical symbol. This is saying P is logically equivalent to Q. It's not like the other symbols. It looks like a double arrow thing, but it's not. Let me explain to you this, and then I promise you'll see examples and you'll understand it. P is logically equivalent to Q Okay? If and only if I write down P, and then I do a double arrow here, and then I do this. Now let's go to our cheat sheet and remember what this symbol is. This symbol says if this is a 0 and this is a 0, then it's true. If this is a 1 and this is a 1, then it's true. They both have to be the same. They can't be this is 0, this is 1, this is 1, this is 0. Okay, so hold on. P is logically equivalent to Q if and only if P by implication is a tautology. What does tautology mean? There's always going to be ones down there. Okay, so what does it mean to say that these two statements have the same truth table? It means if you make a truth table and here you have this and here you have that and you use that line which says they're the same, you're going to get all ones, which is a way of saying it's a tautology. Let me give you an example and we'll do this. Ready? Okay, so you wrote it down. Let's do an example. We have to do lots of examples for this. And then we're going to go through a list of them. Okay, so let's do this. Not R or not S is logically equivalent to not R and S. I'm sorry, let's do it with different letters. I'll show you why in a second. Because it's something we saw already. So, if you're not a Democrat, or not a boy, okay, then what are you? That's logically equivalent to being, it's false that you're a Democrat and a boy. Let's go through that again. If you're not a Democrat, if you're a Republican or a girl, that's the same thing. If you're a Republican or a girl, that's the same thing as saying it's false that you're a Democrat and a boy. Okay? Now, I'd like to show you that this is in fact true, and so we have to go to the definition, and so we have to do it like this. You ready? Not D or not B. By implication, that's a logical formula. Okay, that's a logical formula. It's false that D and B. Okay, great. Two variables. It's going to take us 1 minute to make the truth table. Let's make the truth table. So we have D and B. We have 0, 0, 0, 1, 1, 0, 1, 1. Okay, let's do it. Okay, not D is 1, 1, 0, 0. Not B is 1, 0, 1, 0. Or is 1, 0, 1, 1, 1, 1, 0. Okay, let's do D and B here. D and B is D and B, you can just look at that, that's 0, 0, 0, 1. Okay, not D and B, that means you flip this, so you get 1, 1, 1,
0.
0. Okay, great. Now we're going to compare this to this. Okay, 1, double arrow 1, they're the same. 1. 1, double arrow 1, the same. 1. 1, double arrow 1, the same. 1. 0, double arrow 0, the same. 1. Okay, so they're always the same. Another way of saying it is, this is equal to this. They're both, no matter what you put in for D and B, you're going to get out the same for D and B. You're going to get out the same final result. Another way of saying the same final result is, if you put the by implication, they're going to be the same. Okay, great. Okay, so let's erase this. Okay, so that's the definition of what it means for two propositions to be logically equivalent. Now let's do some examples. Okay? Well, some of them you've seen. So not P is the same thing as what?
P.
P. Okay? And we can, again, if you want, we can do this in the truth table. P is 0 or 1. And so not P is going to be, let's do it like that. Not P is going to be what?
0.
Not P, if P is 0, not P is going to be 1. And that's going to be 0. And not of that is going to be 0 or 1, which is the same thing as 0 or 1. So this is the same as this. Okay? This is called double negation. Okay, great. Let's do some others. Ready? P or Q is the same, is logically equivalent to Q or P. I like ketchup or mustard is the same as saying I like mustard or ketchup. It's the same thing. Okay? P and Q is logically equivalent to Q and P. I like mustard and ketchup is the same thing as saying I like ketchup and mustard. Okay? Next, we're going to go a little bit quicker because we've seen these before. Where did we see these before? When we talked about sets. We'll get to that in a second, but let's just do some more. P or Q or R, doesn't matter how you put the parentheses, that's the same as P or Q or R. Okay, goes like that. And that's called an associative law. So if you memorize this for logic, it's the same thing. In fact, we did it with sets. We had almost the same symbol. We used that symbol for union. We use that symbol. Anyways, just like you have it for or, you also have it for and. Okay? So associative rule for that. Okay, great. Let's do another one. Okay? There are distributive laws. Distributive laws. Distributive laws. How does it go? It says P or Q and R is the same as, logically equivalent to P or Q, okay, and P or R. Okay, guess what? Just like with sets, it goes the other way too. P and Q or R is logically equivalent to P and Q or P and R. Okay. Now it pays to go through an example of this. Pick 3 properties of things. Boy, Republican, small, and go through and see that this is in fact true. Great. Let's do another 2 rules that we've seen before. Let's do it. Ready? Not P. You know what? We're going to do it exactly like we did it before. Let's go through that again. So, not boy or not Democrat is logically equivalent to not boy and Democrat. Let's go through this. If you're a girl or a Republican, that means you are not a boy and a Democrat. Makes sense. Okay? Are you a boy or a girl?
Girl.
Okay, are you a Republican or a Democrat?
I don't know what that is.
Me neither. Okay, they're both basically the same. You ready? Let's do another one. Not boy and not Democrat. That's logically equivalent to not boy or Democrat. Let's go through that. If you're a girl and a Republican, that means you are not a boy or a Democrat. Okay, guess the name of these rules. They're called De Morgan's Law. Okay, we had De Morgan's laws. We had almost exactly the same with we had this. Remember? S complement union T complement is the same thing. It's the same thing as S and intersection T complement. Okay? Okay, so great. Question. Okay, we'll go through a few more of these in a second, and the book has a whole page of them on page, don't move, on page 62, there's a whole page of them.
Can I move now?
What?
Can I move now?
Don't move. Okay, we'll go through them in a second, but well, the rest of them, or a lot of them, but a question. Why are the rules on page 25, which was about set operations, the same, almost the same, as rules on page 62, which is about logic? Why are the rules almost the same? Why is it the same? Associative law, commutative law, distributive law, De Morgan's law, why is it the same? Okay, and the answer is very simple. The answer is as follows. How did we define union? Well, I said A is a subset, B is a subset. We take the union of them. That's those X, okay, such that X is in A or X is in B. That's the definition. Okay, but I'd like to give you another definition. We could also say it as follows. X such that X is in A or X is in B. Okay? So this is the union of those things. But the main point I'm trying to bring out is the union of two elements was defined by the same operations over here, or. So it makes sense that if this is going to satisfy all these rules, then this operation is going to satisfy all those rules. It makes sense. It's the same thing because we're defining the union using the or operation. It's a logical operation. Let's do the other ones. A intersect B is equal to those X such that X is in A and X is in B. Same operation. Same thing. So because intersection was defined using the AND operation, whatever this satisfies, this will also satisfy. Great. Let's talk about the complement. A complement is equal to those X such that X is not in A. Okay, but let's see if we can put them in a little bit more symbols. This is the same as those X such that not X member of A. There. Okay, not X member of A. So, because complement is defined using the not operation, we expect that whatever this satisfies, this will also satisfy. So, for example, if not P is logically equivalent to P, then A complement is equal to A. Just saying the same thing. Okay, great. Let's go through some more of these rules on page 62. Okay. You want to go upstairs? Thank you. Okay, let's do P or P is equal to P, is logically equivalent to P. P and P is logically equivalent to P. P or 0, what's 0? Something that's always false, is logically equivalent to P. P and 0. Now what is this? This is always 0. This, no matter what the variables are, that's going to be 0. Anything and 0, well, this is only going to be true. And is only true when both sides. So this is logically equivalent to 0, because this will always be true. False. Okay? These are called idempotent. Again, we saw them with union. Okay, so we had an intersection, so A intersect A is equal to A. We saw things like that. Okay, great. Let's just finish this thing off. P and 1. This is something that's always 1. This is logically equivalent to P. Okay, and P or 1, whether it's here or here, this is always 1. Well, then this is definitely always 1. Okay, great. Okay, some more from page 62. Sorry, all those that were called, all those things I just erased over here, all 4 of those are called identity rules. Let's do another one. R arrow Q is logically equivalent to not R or Q. Again, this is one statement, this is another statement. They're different statements, but if I made a truth table, and I did this about a half hour ago, I made a truth table for this and I made a truth table for that, it'll be the same thing. One more, and this one we will do a truth table. R arrow Q is logically equivalent to, you ready? Not Q arrow not R. Okay? Let's show that this is true. We're going to show that this is true by showing that they're the same truth table. So instead of writing that out, instead of putting in the by direction, let's just write it out. So element PQ goes first, R goes next. So we always have to do that in alphabetical order. 0, 0, 0, 1, 1, 0, 1, 1. Okay, let's do this. R 0 arrow 0 is 1. 1 arrow 0 is 0. 0 arrow 1 is 1. 1 arrow 1 is 1. Okay, great. Let's do not Q. Not Q is 1, 1, 0, 0. Not R is 1, 0, 1, 0. Okay, great. Now let's do the arrow. 1 arrow 1 is 1. 1 arrow 0 is 0. 0 arrow anything is 1. 0 arrow anything is 1. Notice this truth table is the same as this truth table. Okay, we did this with a few examples. If it's raining, then there are clouds in the sky. That's the same thing as if there are no clouds in the sky, then it's definitely not raining. If you study hard, you will get a good grade. That means if you do not get a good grade, you did not study hard. It's logically equivalent. Not the same words, but they're not logically. If you don't go to sleep on time, you're not going to be able to wake up on time. That means if you did not wake up on time, you did not go to sleep on time. Little girl. Okay, a few more of these rules. Okay, this is one that this is just a strange one, so that's why I picked it. Okay, let's do it. P arrow R, round brackets, and this is number 12 on the list. Q arrow R on the list. This is logically equivalent to P or Q arrow R. Okay, let's just, now again, you can do a truth table for this, but let me just give you an example and you'll see what it means. If you have 4 quarters, you can buy French fries. If you have a dollar bill, you can buy French fries. That's the same thing as, if you have 4 quarters or a dollar bill, then you can buy French fries. It's the same exact thing.
For 4 cents you can't get.
4 quarters, 4 quarters. Okay, let's do another one, very similar to this. P arrow Q and P arrow R. Okay, notice here, the second thing was the same, R. So we were talking about French fries. Okay, here the first thing is the same. Okay, what is this logically equivalent to? Okay, it's logically equivalent to P arrow Q or R. Oops. Okay, hold on. Okay, let's do this. If you study, you're going to know sets, and if you study, you're going to know logic. Okay, test coming up. Let's do that again. If you study, you'll know sets. If you study, you'll know logic.
If you
That
watch
means
this video,
if you
you will know how to
study,
do it.
you'll know sets and logic.
If you watch this video, you know how to.
Thank you from the peanut gallery. Okay, another one in the list, which we already proved, we said was a tautology. This is an example of a tautology. P double arrow Q, if and only if P arrow Q and Q, oh I'm sorry, this wasn't Q arrow P. Okay, P is the same as Q, means P implies Q and Q arrow implies P. Don't confuse this symbol and this symbol. This means this is logically equivalent to this. This means that, really. Okay, one more, two more. Zero arrow P is logically equivalent to 1. Okay. At zero arrow anything, this is always going to be true. I'm sorry, this is always going to be 0. Zero arrow anything is 1. So that's another thing that's always going to be 1. Okay, and one last one. P arrow Q is the same thing as, logically equivalent to, if P is true and Q is false, that implies 0. Okay, if P is true, if P implies true, I'm sorry, if P implies Q, then if P is true and Q is false, that implies contradiction false. Okay, great. One more definition and a few more examples. And then a little girl's going to sleep. You ready?
No.
I think so. Definition. Given two compound propositions. This is just like before, given two compound propositions, P and Q, comma, we say, okay, so far it's the same, but before we were talking about logically equivalent. Now we're not talking about logically equivalent. We're going to talk about logically implies. We say P logically implies Q if P is true. If, okay, so we're defining this. What does it mean logically implies? If P is true, then Q is true. Again, the book gives a definition slightly different, but it's the same thing. Okay, we write it as follows: P single arrow Q. I mean thicker single arrow. So make sure everything is getting in there. Okay, great. Okay, let's say it another way. Okay, so whenever this is true, this will also be true. They're not logically equivalent, but whenever P is true, Q is also true. Another way to say it is P it logically implies Q if and only if, another way of saying it, P arrow Q, that's a logical symbol. And this is true whenever this implies this, is a tautology. Okay? Okay? So it's almost the same. Logically, a logically equivalent means it goes the other way also, it goes the other way, and this will go the other way. So this is not going both ways. One implies the other. I'm going to go through a few examples of these and how do you use it. Okay? So let me show you the most important example, two of the most important rules in all of logic. Ready? If P, this is called modus ponens. Ponens. Okay? Ponens for the word modus is in modus operandi. If you ever watch a detective show, you have modus operandi. Modus means the way, ponens means pushing. It goes as follows. If P is true and P implies Q is true, let's say you know P is true and you know that P implies Q is true. What do you know?
They're both true.
No, well, yes, you know that Q is true. Okay, let's see. So let's go through that again. Here's one statement, and here's another statement. If P is true and P implies Q is true, then whenever that's true, this will also be true. Let's use the arrow to do it. Okay, let's make a truth table. P and P arrow Q. Arrow Q. Okay, let's do this in the truth table. So we have P and Q and 0, 0, 0, 1, 1, 0, 1, 1. Okay, and so this is 0, 0, 1, 1. This is what's that? Okay, this is 1, 1, 0, 1. Okay, now let's do AND of it. 0 and 1 is 0. 0 and 1 is 0. 1 and 0 is 0. 1 and 1 is 1. Great. Now let's do Q. Q is very simple. 0, 1, 0, 1. Now, this final row is not the same as this final row. They're not logically equivalent. If Q is true, it doesn't mean that P is true and P implies Q. No, it doesn't go the other way. It goes this way. You're pushing it forward. Okay? But one thing I can tell you is if this implies this, which means 0 arrow 0 is 1. 0 arrow 1 is 1. 0 arrow 0 is 1. 1 arrow 1 is 1. It's a tautology. Okay, great. Let's just say it again. If it's raining, and raining implies clouds, that means there are clouds. That logically implies that there are clouds. Now again, it doesn't go the other way. Just because there are clouds doesn't mean it's raining, and raining implies clouds. It goes one way. Let's do another one. Sorry, let's have to rewrite the whole thing. Okay. Another important rule is modus tollens. I'm not spelling it right. You look up how to spell it. Okay? Basically says if P implies Q is true. Let's talk about clouds. If it's raining, then there are clouds in the sky. And not Q. Q is false. So P implies Q and Q is false. What can we say? The only thing we can say is it must be that not P. Let's go through that. If it's raining, then there are clouds in the sky. There are no clouds in the sky. What can you say? It's not raining. Okay, let's make a truth table out of this. Okay, let's put that single arrow there. Let's make a truth table. So, variables P, Q, 0, 0, 0, 1, 1, 0, 1, 1. Okay, then P arrow Q is 1, 1, 0, 1. Not Q is 1, 0, 1, 0. And is 1, 0, 0, 0. Great. Not P is 1, 1, 0, 0. Okay, question. Does this is not the same as this, but it implies it. Ready? 1 arrow 1 is 1. 0 arrow anything is 1. 0 arrow anything is 1. 0 arrow anything is 1. It's a tautology. Okay, so here are two examples of one logical statement implying another. Let's go through 4 other examples. I'm just going to state them. P, double arrow, P or Q. If P is true, then P or Q is true. Let's say, if the Mets are good, then the Mets are good, or the moon is made out of green cheese. Okay, the moon is not made out of green cheese, but listen to the statement. If the Mets are good, if you assume the Mets are good, then the statement, the Mets are good or the moon is made out of green cheese, is true. Okay, this is called addition. Addition is like adding, but addition because you can add this extra thing. Once you have something that's true, you can add another thing. Let's do another one. P and Q implies P. Look, let's say I tell you 2 facts. P is true and Q is true. The Mets are doing good and the Yankees are doing good. What can you learn? The Mets are doing good. Okay, this is called simplification. Simplification. You simplified. Look, I don't need to know about the Yankees. I just want interested in the Mets. Okay, let's do another one. P arrow false logically implies not P. Look, if I assume P and I get a contradiction, that means that P is false. This is called absurdity. If you say the moon is made out of green cheese, that gives me a contradiction. Okay, then the moon is not made out of green cheese. Okay, modus ponens, modus tollens is also in there. One more, and then we stop. P or Q. And let's say I tell you either the Mets are doing good or the Yankees are doing good, and not Q. And then I tell you, okay, let's do this again. Either the Mets are doing good or the Yankees are doing good. And then I tell you the Yankees are not doing good. What does this imply? That implies that the Mets are doing good. Let's do that again. If I tell you one of these are true, could be both, but one of them is true. This or this is true. And this is not true. Q is not true. That means P is true. And this has a name that you have to know. Disjunctive. Because this is a or, is really called disjunction. Okay? Syllogism. Syllogism. Okay? Brings it together. Okay? It's a logical rule. Okay, all these rules are on page 63. You have to know the names. Okay, good. Okay, and that is the end of chapter 2. Okay, so that's an introduction to logic. We now skip to section 13.1, 13.2, where we talk more about those quantifiers, the for all and the end. Okay, have a wonderful day.